Have you ever, like, felt this weird thing where the chips that power everything, our computers, phones, like, our whole digital world feel kind of
If
hidden?
you didn't.
Yeah, like it's all built on someone else's proprietary Lego set, you know? They've got the instructions locked up, and we're stuck just building what they allow. Ever hit that wall with, say, x86 or ARM
Okay.
architectures? The restrictions, the licensing fees, the technical limits, they can really stifle innovation, don't you think? And even hold back our own, like, technological independence.
Oh, absolutely. It's like for so long, the blueprints for how our computers think have been under wraps. And yeah, we've made amazing tech, no doubt. But that tight control, it definitely creates choke points, limits what we can truly do in hardware.
Right. So what if, and stick with me here, there's a totally different path. What if we could shake things up? That's where RISC-V comes in.
RISC-V. Sounds a bit sci-fi, doesn't it?
It does, right. But it's far from fiction. It's a potential game changer. And we're not talking about just a new chip design. RISC-V is an open source ISA, an instruction set architecture.
Ah, the ISA. That's the core language, right?
Right.
The bridge between hardware and software.
Exactly. And RISC-V. It's built to be modular, efficient, adaptable, like perfect for everything we're doing now. AI, tiny embedded systems, edge computing, even achieving technological sovereignty, it's all on the table.
You're right, it ticks a lot of boxes. And it's not some overnight fad either. RISC-V has serious academic roots. Started back in 2010 at UC Berkeley.
Berkeley, as in the home of, like, free speech and all that.
The very same. And the idea was to open up hardware design, make it accessible, not just for university research, but for industries to tailor their own solutions. Imagine hardware evolving freely alongside software. Wouldn't that be something?
That's the dream. So for our deep dive today, let's be clear. We're here to figure out why RISC-V matters to all of us, techie or not. We'll get into the specifics, keep it clear and relevant. No jargon overload, promise.
And just so everyone's on the same page, let's nail down what ISA, that instruction set architecture, actually is.
Good point. It can sound intimidating.
It's really not. Simply put, it's the whole set of instructions a processor understands, like the commands it can execute. It's the translator between your software and the physical hardware making it all happen.
So like the vocabulary and grammar of how software talks to the processor.
Perfect analogy. Now let's get into what makes RISC-V so different from, say, the ubiquitous x86 and ARM architectures we're all used to.
Yeah, what's the real shift here? Why is everyone so excited about RISC-V?
Well, the key difference is its openness. It's free.
Okay.
Totally different from x86 or ARM, which are proprietary, bound by patents and licenses. With RISC-V, anyone can design, manufacture, sell hardware based on it. No legal hurdles, no hefty royalties. Universities, startups, huge companies, everyone has a level playing field.
So no more gatekeepers stifling innovation. That sounds pretty revolutionary.
Exactly. It unlocks a massive wave of potential. And it's not just being free. RISC-V is modular to the core. It starts with a really sleek, efficient base set of instructions. You'll hear terms like RV32i, RV64i, RV120i. That number basically indicates the building block size, how much data it can handle in one go.
Okay, so bigger number, more power, generally.
You got it. And from that minimal core, you can add standardized extensions for extra abilities, or even design your own custom instructions for very specific needs.
Wait, custom instructions? That sounds insanely powerful, like fine-tuning to the max.
Oh, it is. This modularity, this ability to extend, it gives you incredible flexibility. You can optimize a RISC-V processor to be super efficient for a particular job, like a tiny microcontroller for a sensor needing minimal power, or a massive supercomputer crunching data for research. RISC-V scales to fit.
That's wild. So you're telling me it can be both incredibly tiny and super powerful.
Precisely. And the entire design is open, fully documented. It's a fantastic tool for education, for really understanding how processors work at their most fundamental level.
Open, adaptable, great for learning. RISC-V is sounding more and more impressive. But let's rewind a bit. How did this all come about? It didn't just appear out of thin air, right?
Not at all. It started in academia, like we said, UC Berkeley around 2010. Key players were Krista Yasanovich and David Patterson, who, fun fact, also co-created the original RISC architecture way back.
Whoa, so this is building on decades of knowledge.
Exactly. They wanted an open ISA for research and teaching, free from the complexities and restrictions of the existing commercial stuff.
Makes sense. A pure academic pursuit, at least initially.
Right. But its potential was clear. It grew into a global collaboration, researchers, engineers, companies, all working together. And in 2015, RISC-V International was born. This nonprofit now manages the development and adoption of RISC-V, ensuring its open evolution. It's really a testament to the power of open collaboration in hardware.
That's amazing. So we've got the what and the why of RISC-V. Now let's peek under the hood just a bit. You mentioned base instruction sets and extensions. Can you break that down a bit more? Like, how do these pieces fit together?
Sure, think of the base ISA, like RV32I, as the foundation, the minimum instructions for a processor to function. Then you have official extensions, adding specific capabilities.
Add-ons.
Exactly. For example, M adds multiplication and division, crucial for most calculations. A brings atomic operations, vital for handling multiple tasks at once and keeping data safe in multi-core processors. F and D are for floating point math, essential for simulations, graphics, anything heavy on calculations. C introduces compressed instructions, making code smaller and more energy efficient, perfect for embedded systems where power is limited.
So each extension has its specific purpose.
Right. Then there's V for vector instructions, also called SIMD, which stands for single instruction, multiple data. This allows one instruction to act on multiple data pieces simultaneously. Super important for AI and media processing.
So it's like doing things in parallel much faster.
Exactly. And Ziggers provides access to control and status registers. Think of it as fine-tuning the processor's behavior for very specific tasks.
Wow, that's a lot of options. So you build what you need, nothing more, no bloat.
That's the beauty of it. This modularity makes RISC-V incredibly efficient. And beyond the official extensions, you can even define your own custom instructions. Say, if you're building a chip for cryptography, you can add instructions to speed up encryption and decryption. Or for image processing, instructions optimized for common image manipulation tasks.
That's like next-level customization. You're not just using a processor, you're shaping it.
Precisely. And this is a major reason why RISC-V is gaining traction in so many different areas of computing.
So it's not just a cool idea, it's actually being used. Can you give us some real-world examples of RISC-V in action?
Absolutely. The adoption is actually quite remarkable. It shows how strategically important RISC-V is becoming globally.
Yep.
Take Alibaba, the Chinese e-commerce and cloud giant. They're developing their own RISC-V chips for data centers and AI. This isn't just saving money, it's about gaining control over their core infrastructure. Could be a huge shift in the industry.
It's like they're taking ownership of their tech destiny, right?
Exactly. Then you have Western Digital, a major data storage company in the U.S. They're switching millions of their microcontrollers to RISC-V. They cite efficiency and flexibility as key reasons. That's a big move, shifting away from established architectures.
Shows a lot of confidence in RISC-V, doesn't it?
It does. And it's not just the big players. C5, a startup founded by RISC-V's creators, is now offering commercially available custom RISC-V processors. This proves its commercial viability. Even NVIDIA, known for graphics processing, is using RISC-V cores in their graphics card controllers.
Wow, NVIDIA using RISC-V, that's a big endorsement.
It shows how versatile and efficient RISC-V is, even for specialized parts within larger systems. And on a national level, governments like India and the European Union are embracing RISC-V for their digital infrastructure. They want more control over their core technologies, more technological independence.
Yeah.
These real-world examples really highlight how RISC-V is moving beyond niche and into the mainstream.
This is getting me really excited about the future of computing. Now, for those of us who aren't hardware engineers, can we get a simplified peek under the hood? I'm curious about that assembler example you mentioned.
Of course. Let's look at that 3-line code snippet. Add assembly. Add by 1, x0, 5 by 1 equals 5. Add by 2, x0, 10, x0 by 2 equals 10. Add by 3 by 1 by 2 by 3 equals by 1 plus by 2 equals 15. Each line is a basic instruction the RISC-V processor can directly execute. Adding means add immediate, adding a constant value to a register. X0 is a special register always holding 0. So the first line is essentially setting a register by 1 to the value 5. The second line does the same, setting by 2 to 10. The third line just adds the values in by 1 and by 2, storing the resultant by 3. 5 plus 10 equals 15, and that's stored in by 3.
Okay, even I could follow that. It is surprisingly clear.
That clarity and simplicity are intentional design principles of RISC-V. It's meant to be easier to understand. This helps both beginners learning low-level programming and engineers designing the chips. Each instruction has a specific, well-defined task, reducing complexity.
So if someone wants to start experimenting with RISC-V, what tools do they need? Is it expensive, needing specialized hardware?
Not at all. There's a great range of tools for all levels. For beginners, there are fantastic web-based simulators like Venus. They're very user-friendly, no software to install. You can get a taste of assembly programming and see how RISC-V instructions work. Then there's RARS, a more feature-rich simulator running on Java, with a graphical interface for stepping through code and examining the processor's state.
So you can start simple and then go deeper as you learn. What about more advanced users, the ones who want to really get into the nitty-gritty?
For them, there's Spike, the official simulator used to verify the correctness of RISC-V hardware. It's a key tool for designers and researchers. If you want to emulate entire operating systems on a virtual RISC-V machine, there's QEMU. And for professionals designing RISC-V hardware on FPGAs, there's Verilator and Chisel for simulation and synthesis. Sci5 also offers complete development environments like Freedom Studio, with everything you need to build, debug, and deploy software on RISC-V systems. The takeaway is there are tools for everyone, from beginners to experts. RISC-V is surprisingly accessible.
This is great news for anyone wanting to dive in. Now, for our academically inclined listeners, the learners who love to really understand the fundamentals, what kind of activities can they do with RISC-V?
There's so many possibilities. One is to really analyze the base RV32I instructions and figure out how to combine them to design the core of a processor, specifically the arithmetic logic unit, or ALU.
So like building the brain of the processor from scratch.
Exactly. Then try implementing basic algorithms like addition, searching, sorting, using RISC-V assembly language. This gives a really concrete understanding of how software talks to hardware at the lowest level.
That sounds like a great way to learn by doing.
It is. You can also simulate instruction execution cycle by cycle using tools like RARs, watching how registers in memory change. If you're more hardware-focused, you can design and build a minimal RISC-V CPU on an FPGA using Verilog or Chisel.
So you could actually create a physical RISC-V chip.
You could. It's a very hands-on experience.
Correct.
You could also compare RISC-V with ARM and x86, looking at performance, power consumption, and the whole openness aspect. And for the software folks, building a simple compiler that translates high-level code into RISC-V assembly is a fantastic project.
Wow, so many options. It really goes beyond theory and into practical application.
Exactly. It helps you grasp how computers actually work at their core.
This is so inspiring. So to sum up, besides the examples we've already discussed, where else is RISC-V being used? What are some of the key areas where it's making a difference?
RISC-V is so versatile, it's popping up everywhere. In the Internet of Things, its efficiency and customizability make it perfect for all those tiny, low-power devices we're seeing everywhere. In embedded systems, where power and size are limited, RISC-V is ideal for designing specialized microcontrollers. Even artificial intelligence is seeing a lot of interest in RISC-V for designing instructions that can speed up machine learning tasks.
So from tiny sensors to powerful AI, it's got it covered.
Yes. And of course, it's becoming a vital tool in education, teaching computer architecture. And even in huge data centers, RISC-V is being explored as a potential alternative to ARM and x86 servers.
So it could be powering the internet one day. That's incredible.
It's certainly a possibility. And surprisingly, it's even being considered for controlling quantum computers. This shows its adaptability and potential in cutting-edge fields. The sheer breadth of applications is a testament to how transformative RISC-V could be for the entire computing world.
It really feels like a new era is dawning. As we wrap up our deep dive, what are the most crucial takeaways you want our listeners to remember about RISC-V?
The key thing is, RISC-V isn't just an improvement, it's a fundamental shift in how we approach hardware. It's about democratizing access to this technology, fostering open collaboration, and ultimately promoting greater technological independence.
So it's about more than just building better chips. It's about empowering everyone to participate in shaping the future of technology.
Exactly. For educational institutions, it's a phenomenal tool for learning. For industries, it's a way to create unique products and break free from dependence on a few big companies. And for governments and communities, it's a path toward greater technological sovereignty.
It's about taking control of our technological destiny, both individually and collectively.
Precisely. Embracing RISC-V is an investment in a more open, accessible, and innovative future for hardware. It's about applying open-source principles to the very core of how computers work.
That's a powerful thought. Thank you so much for taking us on this deep dive into the world of RISC-V. It feels like we've only just begun to explore its possibilities.
It has been a pleasure discussing this with you. And yes, the journey has just begun.
And for our listeners, if this sparked your curiosity, I encourage you to dive deeper, explore the resources we've mentioned, and see where RISC-V takes you. This is a wave worth writing, folks.